been a professor of electrical engineering here at the University of Tennessee for the past 12 years, and over that time I realized that I learn as much from my students as they learn from me. So when I began preparing this presentation, I thought, how would my students explain power electronics to an audience of academics from various disciplines? So, much as they would, I looked to modern productivity tools to help enhance my impact. See, the trouble with explaining power electronics is that it's ever present and impacts a lot of our daily lives, but the underlying technologies are quite complex and hard to see how they're impacting things. It was at this point that I, staring at my over-phalangeed hand, decided that I would not use ChatGPT at all for my presentation, and instead would attempt to explain power electronics by examining how the query I was trying to send is actually enabled by power electronics technologies themselves. Staring at my phone and looking just below the surface, I could see power electronics technologies make up a majority of the circuit board space within my cell phone. These power electronics converters need to be individually designed in order to supply precisely regulated voltages to the individual components within the cell phone, things like the screen, radios, and different sensors. And miniaturization of these technologies allows the miniaturization of my cell phone. A large component within the cell phone is the wireless coil, which allows contactless charging and a seamless charging experience. This technology will soon be distributed to many mobile electronics, allowing us to have a wireless power revolution comparable to that of wireless data before it. Speaking of wireless data, my query is being sent back to the ChatGPT servers through a wireless network enabled by power electronics. Power electronics powers both the transmit and receive radios, and although the 5G revolution is allowing more efficient energy communications, the continued growth in the number of devices communicating on wireless networks continues to increase the energy consumption. But that pales in comparison to the energy consumption of the data centers themselves, which have been growing recently due to online services and increased rapidly due to AI. Modern data centers are consuming as much electricity as many small nations and only continue to grow. Those data centers themselves are enabled by power electronics, and while processors and GPUs are the brains of a data center, power electronics might be every other organ, with 5 to 6 conversion stages in between the grid and the eventual computation equipment. Looking at the core of an AI data center, something like a GPU, the majority of the circuit board is made up of power electronics that are there to supply the thousands of amps necessary to obtain high-speed computation necessary to train modern AI models. One second. These modern GPUs have an energy density rivaling that of commercial scale nuclear reactors. This comparison is made even more apt by the fact that future generation AI data centers promise to consume as much energy as an entire grid scale nuclear reactor. In order to continue the deployment of these types of technologies, we need to revolutionize the grid, and that's again enabled by power electronics. The base load can be supplied by things like nuclear. We have variable generation from renewables and variable loads from data centers, and we need large-scale energy storage in order to instantaneously balance the power mismatch between these, all interfaced through power electronics. One possible source of energy storage that can make up this difference, and another technology rapidly rising up this energy consumption list, is electric vehicles. Though outpaced by data centers, electric vehicles are also among the highest energy consumers in recharging the batteries. Using electric vehicle batteries as the grid backup will allow us to handle this mismatch between source and load generation. Predictions state that within the next 5 years, the residual energy capacity of not-in-use electric vehicle batteries will exceed the needs for the grid. Looking inside these electric vehicles themselves, we again see they're enabled by power electronics. A multitude of power converters, including things like the motor drive that supply the traction power from the battery to the motor in order to motor the vehicle, as well as various accessory power conversion modules powering the different sensors and the computational equipment on a modern vehicle. Again, wireless power technology is being researched for electric vehicles, with a recent demonstration of powering a Porsche Taycan at Oak Ridge National Lab, showcasing that it can be powered wirelessly with comparable power and efficiency to wired charging. This technology continues to advance from powering an electric vehicle in the garage to powering electric buses at bus stops to eventually in-motion wireless charging of vehicles on major thoroughfares, representing a large-scale distributed grid-ready energy storage technology with bidirectional power flow capabilities. Whether looking at electric vehicles, data centers, mobile electronics, or a modern smart home, these are all enabled by various power conversion stages, and each of these power converters needs to be individually designed for the specific task at hand. The process of designing power electronics is a complex interplay of circuit analysis, thermal design, cost analysis, mechanical analysis, all to arrive at an optimal circuit, control pattern, and modulation function. In each of these applications, we need to be able to design the system that best supplements the needs of the application. Here at the University of Tennessee, we have one of the largest and most well-known power electronics programs, servicing all of these different applications and training the future generation of students in order to design power electronics for their dedicated task. This is very important because the competing technology is only getting smarter every day. Thank you.